will be recorded. But yes, so it's going to be pretty simple. Do you all have the pre-lecture notes? Someone shared it with me, and I think I'm just going to spend sort of like 5 minutes going through, how should I do this? So I got 3 documents related to 11.1, which is the pre-lecture notes with all the definitions and the concepts, and then the section 1 review. Sorry, the infinite sequences part 1 is just like 5 problems, and then infinite sequences part 2. So the way that I'm going to do this, unless people have other suggestions, is to do the part 1 review first, because those are all pretty simple. Then talk about the lecture notes, and then do the part 2 problems, which are a little bit harder. Should take, I hope, 15-20 minutes total, and then you all get back to your studying. Sound good? Let me share my screen. Okay, so I will share both. So I'm 2 separate users in this chat because I have both a desktop and laptop. I'm going to share both screens so you can switch between whichever one to your own volition, okay? I typically use my laptop for writing in OneNote, and the desktop is for looking over the notes simultaneously. So just look at whatever screen makes the most sense. But, okay, so okay, at the very start, I guess a sequence is just literally a sequence of numbers, right? A1, A2, A3, ... And it can be a finite sequence or it can be an infinite sequence. It sounds really easy. Why is this so hard? We'll get to that in about 2 minutes when we start talking about limits and stuff like that. But we first have a couple of relatively easy problems, I would say. We first have a problem of 1 over n squared. They're just asking you to write out the terms of the sequence. This isn't terribly mysterious, right? This is just 1 over 1. It's typically understood that n is the natural numbers, so it's starting from 1 and going upwards to the integers. But you'd expect this to be 1, 4, 9, 16, so on and so forth. Hopefully this is fine with everybody, right? Do object if there's any confusion. But otherwise, I'll move on. Okay, so the next one is -1 to the n. My handwriting is also notoriously terrible, by the way, so sorry. But this goes from n is equal to 1 to infinity. Okay. Do you understand what this -1 to the n is doing? It might be a little bit mysterious your first 2 times seeing it, but do you know what this is? Anybody?
It creates an alternating sequence.
Exactly. So it's not terribly mysterious at all. If the regular sequence with just n factorial is 1 over 1, 1 over, 2, 1 over 6, or 3 factorial, which is 6, 1 over 4 factorial, etc. The -1 to the n just alternates the sign. So starting with n is equal to 1, -1 to the first power is negative. So the first one's negative, second one positive, and then it just keeps flipping, so on and so forth. I should put commas in between to let you know that this isn't a sum, but this is a comma-separated list of values. Okay, number 3. 2n plus n. This one is a little bit strange because it just seems to be some random stuff slapped together. There's nothing mysterious here that I can tell, but this is 2 to the 2 plus 2, which is 6. I'm terrible at arithmetic. Then 2 to the 3 is 8, plus 2 is 10. There's nothing mysterious here. It's just a power of 2 plus, I guess that's 11. There's nothing mysterious here. And then 2 to the power of 4, which is 16, plus 4, I think is 20. Yeah, these are just basic computations that we're going over just to be on the same page, but you could presumably have done any of this in high school as well, right? We're just speedrunning this. The next one is 1/2, 4/3. Don't worry, we'll get to the epsilon delta stuff in just a second, but I guess I want to just for completion's sake be on the same page. -16 over 5, 25 over 6. Something like this, you just want to take a look at the pattern, right? It looks like the denominators are increasing by 1. It looks like the numerators are, what are these, the squares? Sorry, this is a 4. These are the squares, and it looks like the sign is alternating, right? So that's just every big thing you want to get really, really fast at this, because chances are this is a good format for a test problem. But it looks like this is something like, 1 over n, and I think it's something like n plus... So notice that this is sort of 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. It looks like this one is trailing a little bit ahead, right? So it looks like this is n plus 1 squared over n. Yeah? Anyways, All right. The very last problem for this quick review, and then we'll get on to the good stuff. -4/3, 8/9, -16 over 27. I'm hoping that your sequence problems will end up being pretty easy pattern recognition ones like this, instead of rather painful epsilon delta wrestling. But again, this pattern isn't bad. It looks like this is 3, 9, 27. It looks like it's a factor of 3 every time. And then up here, it's 4, 2, 4, 8, 16. It just seems to be that one of them starts a little bit earlier than the other. So I think this is probably 1 over -3 to the, what is this, n minus 2? Because if this is the first term, if this is the n is equal to 1, then 1 minus 2 is -1, so then it gets raised to the top. And then I think it's something like just n up here. Anyways, problems like these, you just want to do a little bit carefully. I don't think they're terribly tricky. Does anyone have any objections before we move on to the main course about sequences? Okay. All right, I'll take that as a go ahead sign. So I'm looking at the notes right now. I guess this is called the pre-lecture notes, and they're telling you a tiny bit of notation. They're just saying sometimes an infinite sequence might just drop the infinite sign and just say an, right? This is not terribly, I think this is pretty reasonable. But okay, now we get to the good stuff. We're saying that the sequence an converges to some value L if, and this is equivalent to saying an, the limit as n goes to infinity of an is equal to L. And if you look down on the page, they say that is given any epsilon greater than 0, there is a corresponding integer capital N such that if little n greater than capital N, then an minus L less than epsilon. Does this make sense to you? I'm not expecting any yeses, but I want to know where we are at. Did the teacher spend a lot of time explaining what this means? So I'm going to write it on my screen too. So this is the symbol for every. Do you people know this? Do you people know this? These symbols for every and there exists?
No.
Okay. If you're not familiar, then I'm just going to use regular English. Thanks for letting me know. So you'll see those more if you continue taking any math, CS, or engineering. But it's saying for every epsilon greater than 0, and a lot of the time epsilon is chosen to be a small number or an arbitrarily small number. They're saying there exists a big N such that every little n greater than big N is obeys this property where an minus L is less than epsilon. What the heck does this mean? That's this is the definition of convergence. This is something a mathematician just plucked out of a hat about 150 years ago, and everybody decided that it was the perfect definition of a limit. And since then, we've all just been stuck with it. And it's one of those things where the first time I saw it, it looked absolutely horrendous to me. But now I'm on the other side where I can't imagine it being anything else. So we're going to draw a similar picture to what your professor drew, but we're going to try to explain it very step by step, right? So we start with this idea of a limit L. This is sort of the value that a sequence is potentially approaching, right? So if you think about a number line, if you just think about a real number line, and this is A1 and A2 and A3, A4, A5, A6, A7, and it bunches up a ton, right around this point, then this point would probably be your limit L. This is sort of the intuitive notion of a limit that I think pretty much everyone probably has by the time their first week of calculus is done, right? You've definitely talked about limits at some point in the past, I hope. But the question is, why does this really, really strange expression with a bunch of Greek symbols, why does this capture the notion here of a limit? And the idea is sort of presented like this. It's sort of saying that for every epsilon interval you draw, no matter how large or how small, and in particular, how the smaller ones are usually the ones that are problematic. It's saying that after some finite number of these dots, there's going to be this is an infinite sequence, right? So there's a start to it, but there's no end. But the idea is that after a finite number of these dots, the rest of them are all going to be inside this epsilon. That's what it means to approach a limit. So this is you can kind of see where this comes from in this inequality. An minus L being less than epsilon is essentially saying An is within epsilon of L. An is within epsilon of L, right? So this is basically saying if this is an epsilon and this is an epsilon, it's saying that all of the little ANs are going to be within this interval. Do you see that? Do you see that?
Oh yeah, that makes sense.
Right. But this quantifier is super, super, super important. Because I could have an example, I could have a slightly nastier example where I give you something like A1, A2, A3, and then it looks like they're kind of approaching this point, but let's say every 10th value is over here. Let's say every 10th value is a 10, right? And then a bunch more approach, and then a 20 is over here, and a bunch more approach, and a 30, right? The idea here is, okay, we could potentially think of some point L and ask yourselves, okay, does this obey the definition? For every epsilon greater than 0, there exists a capital N such that every a little n after that is inside that interval. If I arbitrarily drew some epsilon like this, is it true that the tail is entirely within the epsilon interval?
No, it's not true.
That's correct. Why is that not true?
Because there's other points
exactly
as it's approaching the tail.
A10, A20, A30, etc. No matter even if these points are getting in really, 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 really close to L, the fact that by the way I define this absurd sequence, it's terrible. But the way that I defined it is saying that every 10th value or something is a little bit outside, is sort of over here. Then exactly, even though the rest of the points approach, where by our definition of convergence or limit, we say that no, it does not approach. But maybe this was just because we chose the wrong value of epsilon, right? What about a value of epsilon, like a massive value of epsilon like this, so that every single one of these points is within this massive epsilon? Well, I would say that, well, if there exists a capital N such that every little n larger than it, everything is within epsilon, right? So did we go wrong somewhere? This epsilon works, but the previous one didn't. So which one is right? Do you see what I'm asking? Sorry, I know this part is really confusing. And the reason why it's so confusing is because this is probably your first introduction to a quantifier. When you say for every epsilon greater than 0, it means that this definition down here needs to work no matter how large or how small epsilon is. So, okay, if this really large epsilon works, that's great. I don't really care about large epsilons, though. I really care about small epsilons, probably. Does this make sense? I don't care if it works for 1 epsilon. I care if it doesn't work for at least 1 epsilon, is another way of putting it. How are we feeling about this?
A bit confused.
Yeah, this is basically probably your first time being introduced to logic and quantifiers as well. And if you go higher in math, you'll see for every and there exists all over the place. And I think it's kind of crazy that your teacher is throwing all of this on you at the end of a calculus chapter. A lot of Calculus 1 courses introduce this notion from the start, but getting introduced to this at the end is almost feels like a bait and switch to me. But the idea here is this is the definition of a limit. It's saying that I need every single epsilon, for every single epsilon greater than 0, I need there to exist a corresponding capital N such that the tail beyond that capital N is within that epsilon. So it's whatever if this definition works for a very large epsilon, right? This large epsilon really isn't very discriminatory. Everything gets inside it. But really the definition fails because when we look at a smaller epsilon, we start to see a bunch of A10s, A20s, and A30s outside of it. Let me think if I can come up with a proper analogy. It's sort of like saying, if you imagine like you're an archer and you're trying to shoot at a target, right? The epsilon is sort of how much error you're allowed to have on your target. It's sort of like how much error you're allowed in your on the dartboard in sort of the output. And the idea is that if they gave you a smaller and smaller output range, and you were able to find some tail of A's, some tail of the sequence that fit entirely within it, then you're golden. But if they shrink if for any size epsilon, you can find an infinite number of stuff outside, then you're screwed. That's the idea. Sorry, let me say that one more time. So this is confusing, right? This is why I didn't want to do this on Tuesday night and wanted to do it now. You can kind of see why this is some pretty difficult stuff. Yeah.
I think I kind of get your analogy.
Yeah, it's, how do you put it? Another way of saying this is basically for any epsilon, like say in the bow and arrow target situation, I need there to be only a finite number of A's that are outside this this target. Do you see that? Do you see that why that's the same thing? This definition is basically saying after a finite number of A's, like A1, A2, A3, ... by the time you get to AN, it's saying that everything beyond here is inside the target so that there's only a finite number of things outside. That's the same as saying if there's an infinite number of things outside, like say every 10th or every 20th thing lands outside, then this target practice is no good. Yeah? Sorry.
I get it.
Yeah.
So then it's like if like the target's like super big, then it's like you wouldn't reach, or putting it into math terms, like you wouldn't reach the limit basically, kind of.
If the target is really big, like this,
or it's like, never mind. I don't really get it.
It's sort of saying no matter how small the target is, there's only a finite number of stuff outside it. If that's true, then the limit exists. Can you think of why? Sorry, I realize that this is probably not going to, give you mastery over this topic in a single night, but I'm trying to say it now so that we don't have to, panically do something similar on Tuesday night. But I want you to take maybe it'll be easier to see based on a second kind of drawing, the one that your professor included in the notes. And by the way, I'm cognizant of time. I know I don't want to run over too long. But this is basically saying if this is your n, and you think about, and this is, I guess, your how the magnitude of your a values. The idea behind a limit L is basically when a bunch of your points get arbitrarily close to this thing. And the definition of a limit is saying that for every epsilon, so this line right here is, this line up here is L plus epsilon. This line down here is L minus epsilon, right? it's basically saying that after a finite number of these dots, the rest of them, the infinite tail, is entirely within them. Right? So if I chose a smaller set of epsilon for this particular example, it still works because there's one dot outside, two dots outside, maybe a third dot outside. But after like this one, every single thing in here is within the range. You see that? So here, I think if this was a 1, 2, 3, 4, this is 5. I think your big N would be 5. So that A6, A7, A8, etc. is all within this narrow range. You see that? Because that satisfies the definition, we say that the limit exists and it converges. Do you see why this picture is capturing the idea, that very terrible definition of a limit?
I think it kind of makes sense.
Yeah, I try to make. Hopefully, you try to see this as visually as possible. You know, again, I'm going to do sort of it one more time, but with even tighter epsilon. With an even tighter epsilon. The idea here is that, okay, it looks like maybe 10 or 12 things are maybe outside it, but passed around, I would say, this point, everything is inside. So this is a notion that your capital N could depend on your epsilon. You know, you sort of are given you're given an epsilon first, and then you're asked, does in capital N exist, such that everything afterwards is within the boundaries. Okay, that's basically the idea of a epsilon limit. Is that terrible? How are you feeling right now?
So epsilon is like a certain number that you can. It's like it helps make a range, right? And for the limit, and like.
Yeah, the hard thing is that epsilon, you have to be able to think of the idea of a limit for every epsilon. Another way of saying that is, given an arbitrary epsilon, is the rest of this statement true? So I realize that this sounds probably like nothing you've ever thought about before, but the big idea here is being able to understand this quantifier for every epsilon. Right? So epsilon is not like, epsilon can be 1, it can be a half, it can be a tenth, but every single one of those potential epsilon values needs to have this condition be true in order for the definition of limit to be satisfied. So I'm assuming that the difficulty is coming from this idea of for every epsilon. Do you all agree, or is that not where the trouble is? Can someone speak up?
I think I agree. Yeah.
Okay. Yeah, that's where the difficulty was for me when I was learning this for the first time. So I think this is ultimately something that you're going to have to slowly, or over the course of the next 3 or 4 days, just have to hopefully try to accept. I'm hoping that they don't ask anything too hard, so don't spend too much time on it. But I do think you need to set the foundation. And I'm just going to quickly read through the rest of these notes and just sort of provide the intuition, right? They have a theorem. So right now I'm looking at the notes, I think at the bottom of the 3rd or 4th page. Sorry, at the bottom of page 1, 2, 3. If the limit of f of x is L. Okay, so it's basically saying if there's some function that goes to infinity and f of n is equal to an. Sorry, the limit as x goes to, oh, I'm sorry. The limit as x goes to infinity, my bad. It's saying that if there's some function that has a limit L, it's true that f of n is equal to an, then it's saying that that's basically like, okay, f of 1 is a, it's basically like, how would you put this? It's basically like a sampling of the points on this function at every integer value of x. But this is basically saying if you already knew that the function was approaching the limit L, then these dots, like a1, a2, a3, dot, 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 these dots also have to approach L. Does that make sense? This should feel pretty intuitive, I hope. Even if the epsilon stuff is confusing you, can you just see pictorially why this is true? Yes, no?
Yeah, it all somewhat has to like approach the limit.
Right. It's basically like riding along this line, right? And you're just like taking a snapshot at every fixed distance. So that's basically the last 3 or 4 minutes of the session. Is I'm just going to say every one of these theorems out loud and draw the corresponding picture to try to convince you why it's true. But it says, okay, the next page, it says limit an is equal to infinity means that for every positive integer m, there's an integer capital N such that little n greater than capital N, then an is greater than. God, this is terrible. This is basically defining when an is equal to the limit of an is equal to infinity. And the way to make this rigorous is basically saying that, okay, if here's a graph, right? And it's basically saying that you give me any positive number m, right? You give me any number, every positive number m. This is basically saying that at some point, if at some point there exists some capital N such that everything beyond it is above m, so this is probably n. If there exists some capital N such that every element of the sequence beyond it is greater than m, then it goes to infinity. And if this is true for every m, right? Because if we drew our m higher in the first place, this would still be true. Now our n is just set over here. And if we had drawn it even higher, then n would just be set over here, right? You see why this sequence is going to infinity? Why this definition kind of represents going to infinity? It's like basically saying that, let's consider a hypothetical ceiling m. The sequence basically needs to break that ceiling, right? That's another way of saying there is no ceiling. Does that make sense?
Yeah.
Yeah, good. I hope so. But one thing to be a little bit wary about is you might have something that temporarily goes up a little bit and then comes back down, right? And you don't really care about the finite stuff in the beginning. You just need to look at the stuff, off in infinity. Is it true that after a certain point, every single thing is above the ceiling? If so, if that's true for every single possible ceiling, then it goes to infinity. Okay.
Oh, that makes sense, yeah.
Right, exactly. So I'm just trying to draw like a picture or give you intuition for every single one of these things. We're getting close to the end, so you can get back to your night. But okay, the limit laws from section 2.3 also hold for the limits of sequences, and so does the squeeze theorem. I assume the limit laws are just like the limit of like an plus bn is equal to the. I think those are just a bunch of limit laws, like the limit of an plus bn is equal to limit of an plus limit of bn. Like it splits up pretty nicely, as you would hope. But okay, so the squeeze theorem also applies. I think that should be pretty obvious just by comparison. Like if you had some sequence of points like this and you were trying to ask yourself whether it approached some limit, well, if you have some sequence of points like above it and you have a sequence of points below it, and you know that both these things converge to 0 or some other number, then this thing also has to converge, right? The picture should make that up pretty clear. Do you believe that?
Yeah.
Good. Okay. So what is this? Next theorem is if an is equal to limit of an as it goes to infinity, if it's equal to L and f is continuous, it's basically saying then the limit as n goes to infinity of f of an is equal to f of L. So gosh, what the heck does this mean? This is basically saying that, okay, so if you have a bunch of points that approaches some limit L, and f is continuous at L, then this is basically saying, sorry, I'm just going to draw a separate function f. limit as f approaches to infinity. So if this is basically your function f, right? And this is your point L, this is basically saying if you have a bunch of points riding towards, like, if these are your points like A1, A2, A3, A4, AN, and these are your points like FA1, FA2, FA3, FA4 on this line, then it's basically saying you can just ride the function until you get to the limit. And that's true because it's continuous. Is that believable? So basically these things down here are your A1, A2, A3, and they're not necessarily evenly spaced. They're converging towards L. But it's basically saying if, it's basically saying if on the input it converges to some L, then on the output it converges to f of L. Does that make sense? Because it's continuous. It's basically just riding the function along until you get there.
Yeah, it makes sense.
Gotcha.
Because it's continuous.
Exactly. Yeah, it's like, that's not a very rigorous argument at all, and the point of today isn't rigorous, right? But it's just kind of like, you can just kind of see it, right? It's just gotta, if these points get arbitrarily close to L, then so do these. Okay, next one. Limit as n goes to infinity of an is equal to 0, then the limit of an is also equal to 0. Yeah, I don't think this one is too crazy. It's basically saying that if an is something that sort of like straddles the line a little bit and goes up and down, such that, so if this is an and this is the absolute value of an, it's basically saying if the absolute value approaches 0, then so does the original. Seem believable enough?
Yeah.
Yeah, and this basically works because the limit, this basically works because the epsilon limit is double-sided, right? There's a plus epsilon and a minus epsilon. If you remember when we drew that image all the way back, gosh, where did it go? All the way back over here, there was both a plus epsilon, L plus epsilon, and there was also an L minus epsilon. And the reason this works is because now that plus and minus epsilon is centered over 0, it doesn't really matter whether these points are positive and negative. As long as the magnitude goes down to 0, the original thing has to go down to 0 as well. Okay. Gosh. Yeah, we're basically at the end here. Do you even want to go over these last things? Yeah, okay, it'll take 5 seconds. Increasing, decreasing are pretty obvious, right? Increasing, it goes upwards. Decreasing means it goes downwards. A sequence is called monotonic if it is either increasing or decreasing. Okay, so that's just either one. And a sequence is bounded above and bounded below if that's also super self-explanatory, right? It basically means that it's stuck between a upper bound and a lower bound. It may or may never actually touch the upper bound, but so long as some upper bound exists, then we say it's upper bounded, and similarly for lower bounded. And the only result on this page that I think is very interesting is that a bounded monotonic sequence, so bounded monotonic sequence implies convergence. Gosh, what do these words mean, right? This is basically saying, okay, let's say you had a function that was going up and up and up and up and up and up and up, right? But you also know that it's bounded. You also know that it has some ceiling that'll never go past and a floor that'll never go past. The idea here is that if it keeps going up and up and up and up and up, and it never goes past that ceiling, of course it has to converge to something, right? This is also because it's monotonic. The fact that it's monotonic means if it starts going up, it's never allowed to go back down. Does this seem believable? Like if you keep going upwards, eventually you kind of like start running out of room. That's what that is saying.
Oh yeah, that makes sense.
Right? So a lot of these things just seem like Greek when you read them, but my hope is that if you draw a picture like we did just here, every single one of them should make some intuitive sense. There's nothing here that I think is outside of the, capabilities of a first year calculus student. But when you read them on the page, it can just totally go over your head until you have maybe someone giving you intuition or you read it long enough for it to make sense. So that's what I'm hoping you get out of the session. Yeah, it's the problems are not as bad as the theory, I would say, in this particular case. right? By the way, if you need to go, please feel free. But just taking a very quick look at the problems, this is all stuff that you can probably do. You probably could have done this even in Calc 1, right? Whereas before we had a continuous x, now we just sort of have a integer n that increases 1 by 1 by 1. But the concept is the same. I would say this goes to like negative a third because the n squared is the dominant term. And here there's a coefficient of negative 1, and here's a coefficient of 3. So the problems, I hope, are not too crazy. Square root of n cubed plus 4n. Well, this is basically n to the 3 halves, and this is n squared, so I would say this starts looking like n to the 1 half, which goes to infinity, right? So I would say that diverges. Okay, let's hear from the crowd. What would we get from n cubed e to the 2n? What do we think about this? What does this go to?
Would it go to 0?
It would. And the takeaway here is that polynomials grow pretty fast, but exponentials grow so much faster than polynomials, it's not even close. That's the big takeaway here. If you were to actually compute some of these values, I won't prove it to you now, but if you were actually to compute some of these values, it will become immediately clear that the denominator dominates after just 1 or 2 terms. Okay, sine n over 3 to the n. What do you say about this? What does this go to? What can you tell me about sine? Is sine bounded?
Yeah, sine is bounded.
Right, but bounded by what?
1 and negative 1?
Yeah, okay, sure, exactly. So this is basically like plus or minus, you can kind of compare this to plus or minus 1 on top with a 3n on the bottom. So what happens to this?
It converges to 0?
Exactly, converges to 0. Exact same idea with this one, right? Just instead of doing it with sine, it's just doing it explicitly with a negative 1 to the n over 2n. But it's the exact same idea. This thing, it flips, which is another way of saying it's bounded by 1, or n minus 1, and the 2n just starts to dominate before too long. There's one slightly interesting problem on this set, which is 2n minus 1 factorial over 2n plus 1 factorial. Gosh, what the heck would you do about this? I think I'm just going to have to write out a term or two, where for n is equal to 1, this is 2 minus 1 over... Is this 1 over 3 factorial? And 3 over 5 factorial? Does that seem right? So it's 2, 4, 6, and 5 factorial over 7 factorial. What happens to this? I think the next one is basically, it's basically like the odds every time, right? 7 factorial over 9 factorial, 11 factorial over, 9 factorial over 11 factorial. What happens to this?
Is it also 0?
I think so. I think so. Basically, every time it cancels out so that you're just left with, this 9 and this 11 would, for example, cancel out to be like 1 and 10, 11, 10 times 11. And the next one would be 12 times 13. So yeah, I think exactly it would go to 0. Okay. Well, that's more or less your review for sequences. Again, my hope is that your professor isn't going to be too crazy about epsilons, but I guess I wanted to do this today because if you try to think about this for the first time on Tuesday night, I think not only is it going to be incredibly difficult, but it's also going to cannibalize your focus on integrals. So I'm happy that you're sitting in and doing it now. Questions?
So essentially, it's like whenever it's like a small, or like it goes to a small number over a big number, it goes to 0, and then like a big number over a small number, it goes to like infinity.
I guess so. Yeah, like, gosh, I wish I could generalize a little bit better. But basically, anytime you can try to simplify it a little bit, maybe try to look for some, I would call it a little bit of cancellation. Like for this one right here, I would say this is something like n squared over n to the 3 halves, right? And you can kind of simplify this to make it n to the 1 half, which, goes to infinity. You're trying to look for the dominant behavior, so to speak, after you try to compare the numerator and denominator.
I guess that makes sense.
Okay. Well, best of luck. I hope you all do well. Yeah. Any feedback from me? Is there anything else I can address right now? Any points of confusion? Feedback for pedagogical style as well is also welcome. I'm a hobbyist. I, help out here and there because I very much care about math education and like teaching. But do let me know if there are things I can improve on or try to make clear. My hope is that a review session like this might supplement your professor's lectures by, giving you the material a second time and hopefully trying to make things more visual, maybe a little bit less formal. I hope that some intuition can be communicated this way.
Yeah, I think that the visualizations were really good for my learning, and it's called. I liked it when you went over like the problems. It helped me see the theorems more clearly. Kind of.
The individual problems, or are you talking about like drawing out each of the theorems?
Oh, like drawing out each of the theorems, yeah.
Yeah. Okay.
Like the situational parts.
Right. I hope that
Yeah.
I hope that is a decent takeaway. But yeah, this will be recorded. It'll be put on YouTube. We ran a little bit long, but hopefully this will help you out. Okay. I guess I'll stop the recording right there, but do let me know if anyone has any questions.